Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Nuclear Models Part 4 from paper Nuclear and Particle Physics. After studying this module, you will be able to understand the following things. Number 1, the basics of cell model. Number 2, knowledge of magic numbers in nuclei. Number 3, the experimental evidences for shell structure in nuclei. Now, nuclear shell model. In this slide, we are going to study the beginning of nuclear shell model, that how the nuclear shell model came into existence. Now, atomic shell model successfully explained the finer details of atomic structure like magicity, energy, etc. So it means it is understood that shell model was perfectly working in case of atoms. In case of atoms, shell model was all about the distribution of electrons in various quantum mechanical orbitals with specified energies, and this shell model of atoms could explain the hyperfine structure of the atoms. In the case of atoms, the shell model was successful in explaining the things because in this case, in case of atoms, the nucleus was at the center, electrons were orbiting around the nucleus in closed circular orbits. So there was electron is having the negative charge, nucleus was having the positive charge. So there was an electromagnetic interaction, which is basically the Coulombic interaction between the electron and the nucleus, which provided the central potential and which is basically required for the explanation of fine structure of atoms. So people thought that nucleons in the nucleus are more or less in the motion in the same way as electrons in the orbit. So if the shell model was so successful in case of atoms, why can't the shell model be applied in case of nuclei? So they thought that nuclear shell model can also do the same kind of thing. But the problem is, in case of nucleus, there is no central potential because there is no negative charge inside it. The positive charges are roaming around. So even if we consider that the neutrons and protons are in motion in closed circular orbits within the nucleus, then there is no central potential, like as in case of atoms. So nuclear shell model was basically suggested independently by M. Mayer and J. H. D. Jensen in 1949. So they basically came up with the nuclear shell model by adopting the concept from the atomic world. Means, as we have seen and as we have learned so far, that atomic shell model was very successful in explaining various hyperfine structures in the atoms. So they took the same concept in case of nuclei. In their model, in the shell model of nucleus, the protons and neutrons are considered to be moving in well-defined closed shells. The shell model accounts for the existence of magic numbers which were 2, 8, 20, 28, 50, 82 and 126. The nucleus with N or and Z equal to the magic number shows extra stability compared to its neighboring nuclei. Nuclear shell model, experimental evidences. We are going to discuss the experimental evidences which led to the development of nuclear shell model. Now here in this slide, on the right hand side, there is a picture showing the average binding energy per nucleon in terms of MeV as a function of mass number. Now in this slide, we can see that there are two curves plotted, one red color, another one with the black color. Black color one is the experimental one, whereas red one is the theoretical one. Now here we notice that much higher binding energy of nuclei with neutron or and proton magic number compared to the neighboring nuclei. What does this mean? That we observe that there are some hinges in the black curve. So it's not completely fitting as suggested by the theoretical red curve, but there are some hinges or some falls from this pattern, which indicates that the binding energy per nucleon at these mass numbers are different than what it should be as per the Bethe-Weizsäcker mass formula. So now here we can see that if we basically track these hinges, that at what mass number they are there, we notice that these hinges appear for those mass number in which either neutron is a magic number or proton is a magic number, or both are magic nuclei, both are magic numbers. So it means from this observation we can conclude that the nuclei in which either Z or N or both are magic numbers, they have more binding energy as compared to the binding energy per nucleon predicted by Bethe-Weizsäcker mass formula. Nuclear shell model experimental evidences. Now another experimental evidence we are going to discuss in this slide, and what is that evidence? That on the right hand side, if we can see, a picture is shown where the isotopic abundance of various nuclei as a function of mass number is given. Here we can see that the curve shows some peaks and some continuous curves. Now if we notice what are the peaks, then we can see that peaks appear to the nuclei in which either Z or N is a magic number, or Z and N both are magic numbers. For example, the first peak belongs to 56 iron. For 56 iron, we can see that for iron Z is 26. So here we can see that first thing we can see that iron has the peak. Second one, there are lot of peaks appear at N is equal to 50, then at Z is equal to 50, then N is equal to 82, and then Z is equal to 82 and N is equal to 126. It means that naturally occurring isotopes whose nuclei contain magic number Z or N have greater relative abundances. So it means the nuclei in which Z or N or both are magic, they are more abundant in nature. It means they are more stable in nature. For example, strontium 88 with N is equal to 50, barium 138 with N is equal to 82, and cerium 140 with N is equal to 82 have relative abundances of 82.56%, 71.66% and 88.48% respectively. So it is also clear from the graph given on the right hand side. Nuclear shell model experimental evidences. So in this slide we are going to discuss the experimental observations which suggest us that nuclei observe shell structure. What are those experimental evidences? One of the experimental evidence is number of stable nuclei with a given value of Z and N corresponding to the magic number are much larger than the number of stable nuclei with neighboring values of Z and N. So it simply means that those nuclei in which Z or N is a magic number, Z and N are magic numbers, they have more stable isotopes as compared to the ones in which Z or N is not a magic number. For example, tin, which has got Z is equal to 50, has 10 stable isotopes, whereas calcium, which has got Z is equal to 20, has 6 stable isotopes. Another important experimental evidence is that neutron absorbing cross section is very low for the nuclei having magic numbered neutron number. It means the nuclei which have got the number of neutrons equal to the magic number, they show very less tendency of absorbing neutrons. Nuclear shell model, experimental evidences. So we continue our discussion about the experimental evidences. Here in this slide, we are going to discuss few more. Now in this slide, we see two pictures. On the left hand side picture, the cross section as a function of neutron number is given for neutron absorption, whereas on the right hand side picture, neutron capture cross section as a function of neutron number is given. So both these pictures are more or less the same, but the details are different. In the right hand side picture, we find that the capture cross section, neutron absorption cross section for nuclei with magic numbers of neutrons have 1 or 2 orders of magnitude less than that other nuclei with similar masses. What does that mean? It means that if a nucleus has neutron magic number, neutron number equal to the magic number, then for that nucleus the neutron absorption cross section is lower by a factor of 2 as compared to the other nuclei with same mass. So here in this picture on the left hand side, we can see that the lines have been drawn for different magic numbers in neutron like 28, 50, 82 and 126, and we find that at these masses the neutron absorption cross section is less as compared to their nearest neighbors. In the right hand side also, we can find the experimentally observed neutron capture cross section in terms of millibond. So here we find the same pattern, that as a function of neutron number, we find that the neutron capture cross section is different for the nuclei which have magic numbers. So here, for example, here it is shown that the continuous curves falls off at 50, 80, 82 and 126. So this is clearly evident, also as 20. Nuclear shell model, experimental evidences. So we still continue with our discussion about the experimental evidences in favor of the fact that nuclei have magic numbers. Now in this slide, again on the right hand side a picture is given in which the neutron separation energy as a function of neutron number is plotted for various nuclei, and our observation is the neutron separation energy goes up and down regularly till the end. What does that mean? It means that neutron and proton separation energy in nuclei having Z or N as magic numbers show a sharp increase compared to their neighbors. So this is what is being observed. Nuclear shell model, experimental evidences. Now up to the previous slide, we have discussed few cases or few experimental evidences in support of magicity in nuclei. Now here there are few more experimental evidences like nuclei with N just one more than the magic number spontaneously emit a neutron. That is, it is very easy to take out one neutron in nuclei having 1 or 2 excess number of neutron compared to their stable structure. For example, stable oxygen structure is oxygen 16. So in case of oxygen 17, there is one neutron, one additional neutron, which can be taken out quite easily. So it means that the nuclei with N just one more than the magic number spontaneously emit a neutron. Same is the situation with krypton 87. So it should be Kr. So Kr for 87, that is krypton 87, and xenon 137. Energy of first excited state for nuclei with Z or N number equal to the magic number are significantly higher than the other nuclei. It simply means that the nuclei in which Z or N is a magic number, those nuclei are very difficult to excite because their first excited state energy is relatively higher than their nearest neighbors. Another important experimental evidence is excitation probabilities of first excited states are low for nuclei with n or z number equal to the magic number. So, it means it is difficult to excite a nucleus to its first excited state, as it is higher in energy for nuclei with n or z number equal to the magic number. Next experimental evidence is quadrupole moment vanish for nuclei with n or z as magic. So, it means it indicates that for nuclei in which n or z is a magic number, for those nuclei quadrupole moment is observed to be 0 or have very small value, which indicates that they prefer sphericity, because quadrupole moment is a measure of non-spherical behavior of the nucleus. Nuclear shell model experimental evidences. So, we continue our discussion with the experimental evidences in support of magic numbers. Now, here again on the right hand side there is a picture shown where the nuclei are plotted as a function of protons and as a function of the nuclei are plotted in the proton neutron chart. On the y axis we have number of protons, on the x axis we have number of neutrons. So, here this black dotted line is shown. This black dotted line indicates the line where all the stable nuclei are there, and away from this dark black line on the upper side or on the lower side there are unstable nuclei. Now, in this line at various places various arrows have been marked like oxygen 16, 40 calcium, 56 nickel, 48 calcium, 78 nickel, 100 tin, 132 tin and 208 lead. So, why these have been marked? These have been marked to show that at these values the nuclei are basically unstable. 3 natural radioactive series decay by lead, with one of them have n is equal to 126. What does this mean? That in the nature we have 3 natural radioactive series in the actinide region, and it so happens that all 3 radioactive series end up in some sort of lead nuclei. So, it means which has Z is equal to 82. So, all 3 radioactive series decay to lead which has Z is equal to 82. Also, out of 3 series, 1 series end up at lead 208 which has got Z and N both as magic number. Energy of alpha or beta particles emitted by Z or N magic radioactive nuclei is larger than from the other nuclei. So, it means alpha or beta particle are emitted by the nuclei which have either N or Z as magic number. Their alpha particle is observed to have larger energy compared to their nearest neighbors. So, students, let us summarize what we have learned in this module. There are few things which have been discussed in this module. So, now we are going to focus on what we have learned. The first thing we have learned is that nuclear shell model is based on the atomic shell model. Second thing which we have learned is that nuclear shell model was proposed by J. Mayer and J. H. T. Jensen. Third important thing which we have learned is that experimental evidences clearly suggest shell structure in nuclei. Another important thing that we have learned in this module is that the magic numbers are 2, 8, 20, 28, 50, 82 and 126. Also, we have learned that the nuclei with N or and Z as magic number show extra stability and extra features compared to their neighbors.